The part 2 we have seen that deflecting torque produced TD2, that is produced between the series magnetic flux and the eddy currents IE1, which is produced because of the shunt magnetic flux. Now this is that part 3. Okay, this is nothing but part 3 of that part 3 of deflecting torque of energy meter. Okay, and in this video we will see that how that net torque will be generated in that net deflecting torque generated in the energy meter. Okay, now some theory we are going to see. Now this is nothing but this is all about that TD1, how it will be generated. Okay, now this series magnetic flux phi SC creates EMF E2 in a disk. Okay, and E2 produces eddy currents IE2 in disk. Okay, that is the. Now this E2 will be proportional to minus of d by dt of phi SC, but we know that phi SC equation, no, minus d by dt of phi SC is nothing but phi SCM sine of omega t minus beta. No, this equation already we know, starting in that previous video we have discussed. Okay, now therefore that E2 will be directly proportional to minus phi SCM, okay, omega cos of omega t minus beta. Now converting this cos into sine, E2 will be directly proportional to minus phi SCM omega sine of omega t minus beta minus 90 degrees. Now the phasor form, E2 will be E2 bar, which will be equal to phi SCM omega divided by root 2 at an angle of minus of 90 plus beta. Okay, this is the about that eddy EMFs E2. Okay, eddy EMFs E2. Now we will write about that eddy current equations. What to say? E2 bar will be equal to E2 bar divided by the Z. The Z is nothing but impedance of that disk. So E2 bar divided by R plus Jx. Okay, which will be proportional. Oh, we will use proportional here. Proportional. Phi SCM omega divided by root 2, because this is nothing but the equation of the E2 at an angle of minus of 90 plus beta and divided by mod Z at an angle of alpha, because alpha we already know, which will be equal to tan inverse of x by r, that is that impedance angle of that disk. Okay, this Z bar R plus Jx will only written in that what to say, polar form. Okay, that Z bar magnitude will be equal to square root of r square plus x square. Okay, that is the thing. Now this IE2 bar will be directly proportional to phi SCM omega divided by root 2 Z bar minus of 90 plus beta plus alpha. Okay, okay, this is that thing. Now you can write this time domain form of this equation. IE2 will be phi is m omega root 2 z bar magnitude sine of omega t minus of 90 plus beta plus alpha. You can write this equation. Now we will go uh, to determine this direction of this IE2. IE2 direction by లేడు బండి లేడు బియ్యమా ఏం బియ్యం అమ్మా చూడు బియ్యం నాగబాబు వచ్చాడు. So IE2 direction by right hand thumb rule, that is IE2 bar produces a flux phi E2 that opposes phi SE. That is how it looks like. We are going to have that disk now, and we are going to have phi SE. This is phi SE, and this side phi SE is going to provide an opposition phi E2 opposite, and here it is going to produce opposite phi E2 like this. Now if you place thumb in the direction of phi E2, we will get that eddy current directions in this way. And similarly here also we are going to get another IE2. This is nothing but this IE2. Okay, in the similar way we can get that by using a right hand thumb rule. Okay, now we will draw that phasor diagram for this above scenarios. Now we will draw the phasor diagrams. Okay, this is that reference phasor, whatever that is there, no 0. This is phi SC bar. It is at an angle of beta, and this is 90 degrees. And E2, already we know that these phasor expressions here. This E2 lags this phi SC by 90 degrees, and IE2 lags by alpha. Okay, that is this phasor diagram. Now we will go that working of that motor. Now what we will do, now apply motor principle. That is, a torque will be produced on the disc because of this shunt flux and eddy current IE2. Okay, that is, whenever a current carrying conductor is placed in a magnetic field, it experiences force in the same way. That is, torque will be produced on disk because of phi sh and IE2. That is, whenever current carry conductor placed in a magnetic field, it experiences force. Here that current carrying conductor is nothing but a disk, and current is nothing but this IE2, and this magnetic field is nothing but a phi sh. Okay, the scenario will be looking as like this. How it will be looking? This is the phi sh, and this is the disk we are going to have. Okay, and here we are having that two eddy currents which are produced because of that series magnetic flux. Okay, and the directions will be IE2 bar and IE2 bar. Okay, now what we will do is nothing but we will apply this Fleming's left hand rule here. Then what is that? Four finger direction is nothing but flux direction, phi sh, four finger. Okay, and this eddy current directions, eddy current directions, which is the central finger. And we are going to get that thumb direction like this. It is an deflecting torque TD1 direction or the force direction. That means here we are going to get that here that force as an TD1. Okay, that means the disk is going to rotate in this way and within force of TD1. Okay, and we already know that previously we have seen that whenever a disk is placed which is carrying an RMS current I and it is producing an RMS flux phi, that torque produced on the disk will be phi into I cos of angle between these two things. The same principle we are going to have. So now similarly this TD1 will be directly proportional to phi shm divided by root 2, because RMS flux of that shunt magnet and also RMS value of that eddy currents. What is that RMS value of that eddy current? Eddy current equation, RMS value. Yes, this is there now. This is nothing but this RMS value. RMS value. What is that? Phi sm omega divided by root 2, and it is nothing but cos of 90 plus alpha plus beta. This is that. This is that deflecting torque equation. Then TD1 will be equal to, this is RMS, and here also this phi is RMS, and this omega is nothing but directly proportional to frequency. Now already previously we have seen, and cos of 90 plus alpha plus beta. Okay, because omega is equal to 2 pi f. Okay, frequency of that all these voltages. Okay, this is how that TD1 will be produced. This TD1, whatever that is there. Now on disk we are having two torques. Okay, two torques. One is TD2 and another one is TD1. How these two torques are there? This is the disk, no? TD2 and TD2, and we are going to have the TD1 like this. Okay. Now net torque on the disk. And average value will be TD2 minus TD1. Okay, and the disk will rotate on which direction that the torque magnitudes are more. If TD1 is more, then a disk will rotate in this direction. If TD2 is more, then disk will rotate in this direction. Okay, that is a simple thing. Now we will substitute the expressions for this TD2 and TD1, and we will write this that net torque equation. This TD2 is nothing but phi sh RMS into phi sc RMS f divided by mod z cos of 90 beta minus alpha, and this is also TD1 now. Phi sh RMS phi sc RMS into frequency f divided by mod z into cos of 90 plus beta plus alpha. Okay, this is the net torque. Now we will use that formula of cos of 90 minus theta as sin theta. Then you can write that cos of 90 minus beta plus alpha as sin of beta minus alpha. And similarly cos of 90 plus theta, 90 plus theta is nothing but so minus sin theta, so this can be written as that cos of 90 plus alpha plus beta can be written as minus sin of beta plus alpha. Okay, now we will substitute these two equations, this equation and this equation on that net torque equation. Okay, that is TD net average value will be equal to phi sh RMS and phi sc RMS f divided by mod z. Okay, and sin of beta minus beta plus alpha, and let us say this as an capital A and this as an capital B. Then sin A plus sin B will be equal to 2 sin of was A plus B by 2 into sin of A minus B by 2. Now by applying these things we will get that TD net average will be equal to, or will be directly proportional here, directly proportional to 2 phi sh RMS into phi sc RMS by mod z into sin beta into cos alpha. Okay, This is the thing we have got. Okay, here in the above equation, that beta is nothing but angle between shunt magnetic flux and series magnetic flux, and alpha is nothing but angle between E1 and IE1 or E2 and IE2. Okay, that is these angles. This is nothing but angle for eddy current paths. Angle for eddy current paths. Okay, so fine, on a final note what we can say, so in energy meter, if angle between shunt flux phasor and series flux phasor is beta, which will be equal to 90 degrees, and impedance offered to eddy current paths. హలో అంతే అప్పడాల ప్యాకెట్ సాంబార్ పొడి అవి ఊరమరకాయలు తీసుకున్నావా అంతే ఆహా సరే అయితే వచ్చి తెలియదులే ఏం సబ్బులు సంతూర్ సబ్బులు అంట సంతూర్ సబ్బులు ఒక 6 వేసుకో చిన్నవి అదే మళ్ళీ షాంపూ ప్యాకెట్లు కూడా అంట హెడ్ అండ్ షోల్డర్స్ షాంపూ ప్యాకెట్లు హెడ్ అండ్ షోల్డర్స్ షాంపూ ప్యాకెట్లు సరే సార్ సబ్బులు తెచ్చి షాంపూ ప్యాకెట్లు తెస్తారే ల్యాబ్ సబ్బులు కూడా వచ్చి నేను తర్వాత తెస్తా that is the impedance offered to the current paths. హలో ఏంటి 10 రూపాయలు కాదు, కొద్ది పెద్దగానే ఉంటాయి, 100 గ్రాములు ఎంత ఉంటాయి ఇక సబ్బులు, 30 రూపాయలు 40 రూపాయలు ఉంటాయి, 30-40 రూపాయలు ఉంటుంది ఒక్కో సబ్బు, సంతూర్ సబ్బు 50. అంతకంటే చిన్నవి ఉంటాయి చూడు, 20. ఏం సబ్బులు సంతూరేనా? సంతే 20 రూపాయలు తీసుకో అయితే. అంతే మా మామిడి దగ్గరేనా? మరి అది సరే కానీ సరే ఇట్టా ఏమైతే ఏమైంది, ఒకసారి ఏమవుతులే. సంతూర్ సబ్బులే అంటారా? That is the current paths is impedance offered to the current paths is pure resistive, then alpha will be equal to 0 because alpha is nothing but tan inverse of x by r. That means x will be 0. So if x is equal to 0, then sin beta will be 1 and cos alpha will be 1. Then that TD net average will be directly proportional to 2 5SC RMS 5SH RMS F divided by mod Z, which will be an max value. Okay, you can remove this 2 and this F also, or this Z also, that is which will be directly proportional to 5SC RMS into 5SH RMS in max value. Okay, max value. And this previous slides also, this TD net average will be proportional to 5SH RMS into 5SE RMS sin beta into cos alpha. That is, in an induction energy meter, the torque, the deflecting torque developed in the disc will be proportional to product of the RMS values of the shunt flux and series flux, and sine of the angle between that shunt flux phasor and series flux phasor, and cosine of the impedance angle of that eddy currents. That is the thing. This is the final statement of that torque equation of that energy meter. Okay. Now let us say. Now the continuation. What we will say is that now say a lag load is connected to energy meter. That means see this there, no, this is the thing. This load, whatever this load is there, no, in that energy meter. Okay, now come to current page. This energy meter VL bar, and this is the current bar IL bar. Lagging load. So a lagging load means let us say that the power factor of that power factor angle of that load is as an phi, which is the angle between VL bar and IL bar, power factor angle. Lagging load of power factor cos phi. Okay, that is this angle. Same that circuits phasor analysis. Then that phasor diagram can be written as then phasor diagram. And we are going to have two cases. Okay, ideal case and it is an practical case. So ideal case means that the angle between VL and phi SH will be 90 degrees. This thing already we have seen in that what to say in a part 1 video. Okay, where ideal case, the angle between VL bar and phi SH bar will be 90 degrees. Okay, will be seen. Okay, the same derivation here it is used. That means we are going to have an VL bar here like this, and this is nothing but the shunt flux phi SH bar 90 degrees, and we are going to have that current lagging now IL bar, and it is an phi. Okay, and this current is there, no, this will be proportional to that series flux, because in series magnet series that IL only created that series flux, no, that's why both are proportional. Okay, and this shunt flux is there, no, it will be proportional to that voltage, it will be proportional, so this will be proportional. Okay, and here you can see that angle between these two degrees will be 90 minus 5. Okay, that is shunt flux will be proportional to that voltage, because that shunt magnet is connected in parallel with that uh, load voltage only, because like this, the shunt magnet that shunt magnetic coil, whatever we are going to have shunt coil, and it is carrying a current I and it is having an voltage VL bar. Okay, and it is producing a flux 5sh, the same voltage here, so here this one will be 5sh. Okay, this thing already we have seen in that part 1 video, and here it will be like this. Now I will go to the next page, I'll add one page, and here it is an ideal case. Okay, I will write, I'll draw one line here. Yes, now we have seen. Okay, and in the practical case, or we'll complete first this ideal case. Okay, we know that basically what to say, and previous slide will go, and 5sh, and we already know that 5sh and IP will be in phase, already we have seen in that paper 1, because IP only created 5sh, that's why both are in current creates flux, that's why IP and 5sh will be in phase. Okay, now we know we know 5sh RMS will be proportional to magnitude of VL. This is an RMS, because VL created IP and IP created 5sh, that's the thing, and 5sc RMS will be proportional to IL. This is also RMS, because IL only created a 5sc, no, that is the thing. Here it is nothing but this is because VL creates IP and IP creates what to say 5sh bar, and here IL creates 5sc, because current creates flux, current creates flux, because current creates flux, and series magnet is connected in series with the load, so that is load and the series magnetic of series magnetic currents, or series magnetic currents and the load currents will be same, because both are connected in series. Okay, then we already know that the torque equation of that energy meter TD net average will be proportional to 5sc RMS into 5sh RMS into sine beta into cos alpha. So this beta is nothing but angle between 5sc and 5 angle between 5sc and 5sh. Okay, see this 5sh and 5s, this angle now beta, which will be equal to 90 minus 5. Okay, 90 minus 5, so that will be proportional, though this will be proportional to mod IL bar, and this will be proportional to mod B, and this will be nothing but sine of 90 minus 5, and let us say this alpha to be 0 for time being. Okay, then it will be 1. Okay, because 0 means that is the resistive paths are what to say, the resistive paths, that eddy current paths are resistive. Okay, This is the thing. This is the thing. This is the thing. Now this can be written as IL and VL, and this is nothing but sin 90 minus phi can be written as cos phi, which will be proportional to true power, true active power in load. That is what we can say is that for ideal case, deflecting torque in energy meter, deflecting torque in energy meter is proportional to true active power of load, that is TD net average will be proportional to active power. So you can write is an K into some constant K into active power in an ideal case. Okay. Now we go to previous page. Now we will say it is a practical case. See, for a practical case, we'll draw the phasor diagram. Now this in practical case, okay. In the practical case, we have already seen. For practical case, the angle between IP and VL is not equal to 90 degrees. Okay, we have already seen in that part 1 of this video. That is, let us say this is an VL, and this is a 90 degrees. This will be IP. So the angle between these two things will be delta, and we already know that phi sh and IP will be in phase because IP only created phi sh now. That's why they're in phase, and that power factor angle, that load current will be lagging 90 degrees by phi. Now the angle between these two will be how much? Delta minus phi, and we already know that IL will be proportional to phi SC. Okay, that is this thing. Here also, in ideal case, VL bar and IP bar will be 90 degrees, and IP and phi SH angle will be 0 degrees. Here also, IP and phi SH will be 0 degrees. We have to proceed in this way. Okay, these two things we have already seen in that part 1 of that videos, how this phasor diagrams came. Now here this will be the beta. Okay, this will be that beta. We'll go to next page. Now here you can write that TD net average will be equal to phi SC RMS into phi SH RMS and sine beta, and let us assume alpha here also 0. This beta here, it is nothing but delta minus phi. Okay, that will be equal to, it will be VL and it will be IL and it will be sine of delta minus phi. Okay, this is an errorish value in a practical case. Okay, that means what does it is happening here is nothing but because here that delta is there now. Whatever delta we are getting is now already you have seen in that part 1 video. This is delta is nothing but XP divided by RP. Okay, XP divided by RP. So if shunt coil is pure inductive, that is Rp is equal to 0, then delta will be 90 degrees. So if delta is equal to 90 degrees, then TD net average will be VL bar IL bar into sine of 90 minus 5, and this will become as an cos 5, that is it will be equal to an ideal case. Okay, this will be equal to an ideal case. So what we have to say here is nothing but because of the observation here we have to note is nothing but because of what we have to say is nothing but here practical case, because of shunt coil resistance the angle between load voltage and phi sh is delta minus phi. The angle between VL and phi sh is a delta, which is not 90 degrees. That is delta is less than 90 degrees. Delta is less than 90 degrees because of shunt coil resistance. So if Rp is equal to 0, then delta will be equal to 90 degrees. That is the thing we have already seen previously. So because of the shunt coil resistance, we are going to get that delta less than 90 degrees, which reduces the TD, because TD will be proportional to sine of delta minus phi. Okay, but ideal case it will be sine of 90 minus phi, no? So this will be lesser. This is an practical case and this will be in ideal case. Okay, so practical TD reduces, deflecting torque TD will be reducing. That deflecting torque is reducing because of that shunt coil resistance. This thing is called as an such type of error. Such type of error is called lag error. This type of error is called as an lag error. Lag error means that is VL and phi sh angle between them is not equal to 90 degrees. It will be equal to delta. It is because of what? Because of shunt coil resistance. Okay, it is because of that shunt coil resistance. Okay, thank you. This is all about that this energy meter deflecting torque equation. So final note we can say, is nothing but that a deflecting torque will be proportional to phi sc RMS and phi sh RMS sin beta and cos alpha. Okay, for ideal case this beta will be equal to 90 minus 5, and for practical case beta is equal to delta minus 5. Okay, here that resistance of that shunt coil will be 0. Here resistance of shunt coil will not be equal to 0. Here that VL and phi sh angle will be 90 degrees. Here that angle between VL and phi sh is not equal to 90 degrees. Okay, that is the thing we have to observe. Okay, that is the thing. This is the basic torque equation. Okay, deflecting torque equation only. Next we have to study about braking torque. Braking torque. And also we have, for an ideal case, we have seen that TD will be equal to K into active power in the circuit. This one also we have already seen. This will be the starting point for braking torque. Okay, that is the thing. Thank you.